let's look at some uses of the relationship between angular and linear velocity. So remember, linear velocity is the radius times the angular velocity. Here we have a circle with center 0, point A that's 25 centimeters from the center, and point B that is a total of 60 centimeters from the center, 25 plus 35. And they're both rotating, and we are given the information that point A has a linear velocity of 80 centimeters per second. So this would be V, right? So V for point A. So we can say then that 80 centimeters per second is equal to the radius that A is from the center, 25 centimeters, times omega, which is what we're trying to find, omega of point A. So all we have to do is divide by 25 centimeters. Okay, so notice the centimeters cancel out, and we end up with 80 divided by 25, which is 3.2 per second, which is our angular velocity. Well, remember, radians are a unitless measure, so this is 3.2 radians per second. Now let's look to see how that makes sense. Remember that every time we move 1 radian, we mark out 1 radius length. Okay, so we can mark out 25 centimeters here. Then we move another radius length. There's another 25 centimeters. Then we move another radius length. That's another 25 centimeters. And then we move 1/5, 2/10 or 1/5 of 25, which would be another 5. So this is altogether, if we go all the way around from here to here, this is V, or this is a linear distance of 80 centimeters, but it is an angular distance of 3.2 radians. It's hard to read there. Now, let's see if I can take that one off and there we go. That's a little easier to read. So 3.2 radians. So you would actually be able to just kind of figure this out logically just by counting radius lengths too. So this is a very logical relationship that we take the number of radians times the radius length and we get the linear distance traveled. And in this case, of course, we're talking about velocity, so we're talking about the speed that of the angular rotation and the speed that is being traveled. Now let's take a look then, what is the linear velocity of point B? So this uses the relationship that we talked about, that we know that if points A and B are on the same rotating object, that points A and B have the same angular velocity. So we know that the angular velocity of B is equal to the angular velocity of A. Now its radius is different, so it's going to have a different linear velocity. So the linear velocity of B is going to be equal to its radius, 35 centimeters, times the same angular velocity that we just calculated, 32 radians per second. Remember, radians is a unitless measure, so this just ends up as being 35 times 3.2 centimeters per second. So the velocity of point B is, oh, not 35, I'm sorry, you're probably crying, half point, it's 60 altogether, 35 more than point A, so 60. So 60 times 3.2 is 192 centimeters per second. Now in our next problem, we're going to be looking at a problem where we don't start out given something in radians per second, but we're given an angular velocity in revolutions per minute. Now revolution per minute, or RPMs, is a typical way that the speed of motors is measured. So a motor is usually something that's spinning and turning. So for example, in a car motor, the motor is spinning. Eventually it goes through a series of gears to spin, to rotate the tires at a certain speed. And you might be, if you're in a car, you might hear a car as you accelerate, you hear the engine change tones. It kind of goes, and you even kind of feel that a little bit as the car changes gears. And if you have a tachometer on your dashboard, you'll see this needle getting higher and higher, and then when the gear shifts, it drops down lower, and then when the gear shifts again, it drops down lower, because the idea is you don't want a whole lot of revolutions per minute in your engine, because that's harder on your engine. So as you accelerate, it changes the car into a different gear, which has a larger radius and therefore a lower amount of revolutions per second. So we're going to see how this happens with a simple example using 2 gears and a belt. So we have 2 gears connected by a belt, and we are given the angular velocity of the little gear in revolutions per minute. Okay, so it says the small gear is going at a revolution per minute of 25 RPMs. Okay, so that's the small gear. Now, revolutions per minute is an angular velocity measurement, but it is not the angular velocity measurement that we can use in this formula. This has to be in radians. Omega has to be in radians, not in revolutions per minute. So the first thing we have to do is change revolutions per minute into radians. So what is the angular velocity of the small gear in radians per minute? Well, what we have to recognize is that 1 revolution is equal to 2 pi radians. So if we have 25 revolutions, is going to be 25 times 2 pi radians. So we have 50 pi radians per minute. Okay, so in other words, going 25 times around every minute. So that's going 50 pi radians in a minute. Now, what's the linear velocity of the belt connecting the 2 gears? Well, what I want you to notice is that the belt is around the outside of both gears. So let's say we have a point that goes from here to here on the little gear. Well, the same amount of time it would take this point to move from here to here would be the same amount of time it would take that point to move from here to here on the belt. So the belt has the same linear velocity as the outside edge of the gear, which means it also has the same linear velocity as the large gear. So the small gear, the large gear, and the belt all have the same linear velocity. So I'm going to write this down. So linear velocity is the same for the belt and the outside of both gears. So that's important to know, because that's going to allow us to go from one to the other. So what's the linear velocity of the belt connecting the 2 gears? We need to know, we know that the velocity of the small gear equals the velocity of the belt, which equals the velocity of the large gear. And I can figure out the velocity of the small gear because I know its radius, and I also know how fast it is traveling in radians per minute. So the velocity of the belt equals the velocity of the small gear, which is the linear velocity, that is, which is its radius, 3 centimeters, times its angular velocity of 50 pi radians per minute. So we can get its linear velocity in centimeters per minute for both the belt and the small gear. So the linear velocity of the belt, which is also the linear velocity of the small gear, is 150 pi centimeters per minute. And just to let you know about how much that is, that's about 471.24 centimeters per minute. But I'm going to stick with 150 pi for future problems because that's the exact value. Okay, now what's the angular velocity of the large gear in radians per minute and also in revolutions per minute? So remember, we know that the linear velocity of the large gear is the same as the belt. So the linear velocity of the large gear is 150 pi centimeters per minute. So, and we also know its radius is 8 centimeters. So we can say 150 pi centimeters per minute is equal to 8 centimeters times its angular velocity. And then just divide both sides by 8 centimeters. And we can find then its angular velocity in radians per minute. So 150 pi divided by 8 is about 58.9 radians per minute. Because it's just, we just get per minute, and so we're going back to radians as a unitless measure. So there is the angular velocity of the large gear. Now I also know, and now I want to do revolutions per minute, so I go back and use my same relationship that 1 revolution is equal to 6.28 radians. So if I know it's going 58.8 radians per minute, I'm going to take the 58.9, divide it by 6.28. That'll tell me how many revolutions, because every time it goes around once, that's 6.28 radians. So that ends up being, and I went ahead and used the exact values here, and I ended up with, actually I divided by 2 pi rather than 6.28. because that's more exact. So I divided by 2 pi. Then the 58.9, I was using the value on my calculator, so I ended up with exactly 9.375 revolutions per minute. So this is in radians per minute, and then that is in revolutions per minute. So what that tells me is that for every minute, the small gear is going around 25 times, but the large gear is only going around 9.375 times. So if we were able to switch, as in a motor, from using the small gear to using the large gear, that would actually be more efficient, not having so much, not having to spin so fast to keep the belt going. And I honestly don't know how that works in a motor. I'm not terribly familiar with how the motors work, but I know that my car switches gears, and I know that's good for the car. Now, what is the linear velocity of the belt in meters per second? All right, so we have the linear velocity of the belt already in centimeters per minute. So this is a matter of changing units. So I'm going to show you a method I used to change units. It's very similar to a method you may have seen in chemistry called dimensional analysis. And you don't have to do it this way, but I find this is a really efficient way, especially when you're dealing with different units. So I know that I have 150 pi centimeters per minute is my linear velocity that I want to change to meters per second. So first of all, I want to change centimeters to meters. Now remember, I can multiply a fraction by 1, and it doesn't change. I can multiply any number by 1, and it doesn't change it. So what I'm going to do is come up with some creative forms of the number 1. So my first creative form of the number 1 is I know that 100 centimeters is equal to 1 meter. So if I make a fraction out of that, that's just the number 1. So I'm going to put 100 centimeters in the denominator and 1 meter in the numerator, because I want the centimeters to divide out. Also, I know that if I take centimeters and divide by 100, it turns into meters. Then I also know that I have how many revolutions per minute, but I want to know how many revolutions per second. So I'm going to have to divide by 60. In other words, I'm going to have to make a fraction that says 1 minute is equal to 60 seconds. And once again, position it so the minutes cancel out. So basically, I end up with 150 pi meters over 100 times 60 seconds. So if I do that calculation, 150 pi divided by 100 times 60, I end up with 0.0785 meters per second. So this is a really efficient way to change units. Later on, you're going to be doing a problem, a challenge problem in homework, if you choose to do it, that is looking at how do you know how fast a bike is going if you pedal at a certain rate with a certain gear ratio. And you just have to, it's very similar to the two problems this problem that we just did, only you're adding in a few extra steps as you go from the pedal to the gear to the chain to the gear back to the tire, and then change some units. So it takes more steps, but it's basically applying these same principles that we've just done.